So in this video, we're going to talk about improper integrals. So improper integrals are a form of a definite integral. And in the three cases that I have up on the screen, you can see one of the bounds would be the infinities. And so because we're introducing now not a specifically defined closed region to where we would be finding the area, we have to be careful with our notation as we introduce infinity, which is not a tangible number that we can just evaluate at. And so to compensate for that and to make things mathematically clear, we introduce the limit notation. So for our first one, right here, we've got the integral from a to positive infinity, our function dx. We're going to translate this now into a limit as t approaches positive infinity from a to t f of x dx. And you'll see as we work some of these examples, the notation is going to allow us now to plug in a t instead of an infinity. You'll never see us plug in an infinity. We may talk about it as a big number being plugged in, but we can't physically plug in infinity. But we'll be able now to evaluate the limit once we have the opportunity to integrate. All right, so for the second one, it's going to be pretty similar. We're going to have this limit as t now goes to negative infinity of the integral t to b f of x dx. And for the third one, we're going to have to be a little bit careful. Because we're bounded by infinities on both sides, we're going to need to split this up into two separate integrals. We'll have the limit as t goes to negative infinity with the integral t to some place, we'll call it c, f of x dx, and then plus the limit as x goes to positive infinity with the integral c to t f of x dx. So we're using several of your properties that you learned back in Calc 1 on how we separated this. We do need to be careful though, because we're studying improper integrals. The c is not just a random c. It certainly can be any number of values, but we need to make sure that it wouldn't create a discontinuity in our function. And that's kind of what this is eventually going to lead us into, is the idea that since we're dealing with infinities or maybe even some form of discontinuity later in the section, we're not necessarily dealing with that defined closed region anymore. And so the book's got a couple really nice pictures in there, starting on page 495, that I'd really encourage you guys to take a look at to better visualize what it is we're actually doing as we take a look at some messier examples. Okay, so as we take a look at our first example, you can see it's pretty similar to one of the formats that I had on the previous screen. And so the first thing we're going to do is just fix the notation. We're going to look at this as a limit as t approaches positive infinity from 2 to t of our function 1 over x root ln x dx. So at this point, all we've done is change the notation, and now we'll just integrate as usual. If we integrate as usual, our u would be that natural log of x, our du would be the 1 over x dx, and it appears to be a nice fit. Now, as I continue down this next step, notice what I'm doing here. Because I'm changing from x's into u's, we know that these values aren't good anymore. And so I can't write anything there unless I change over here. But even if I change over here, then I'm still at the mercy of this limit. So my recommendation for these improper integrals is to just continue down from the previous step to this one, leaving it blank underneath the limit and blank on the bounds. We'll then integrate and convert back into x's, which then will relate us back into these t's. Okay, so it's going to be far easier to do that on most of these problems. Okay, so we'll go ahead and integrate, and if we integrate, that's going to give us a 2 square root natural log of x, and this is being evaluated now from 2 to t, and of course we still have our limit as t goes to positive infinity out front. Okay, so to integrate again, we just add 1 and divide, and then substitute the u value back in. Okay, so now let's go nice and slow through this evaluation process. I'm going to keep my limit notation out there, and then I'm going to have 2 square root natural log t minus 2 square root natural log of 2. So we've done now the integration part when it comes down to the definite integral and applying that fundamental theorem of calculus. Now it's really just a limit problem at this point. And so as we look at this as a limit, you can see if I take a really big number and I plug it into this natural log, that's going to go to infinity. The square root of infinity is infinity. Infinity times 2 is still positive infinity. So this whole piece right here goes to positive infinity. And this is just some constant over here. I don't know what it is, but it's just a constant. And when we could take infinity minus some constant, it's negligible. Therefore, our end result would be a positive infinity. So we would actually say that this improper integral diverges. You'll hear the words diverge and converge thrown around quite a bit starting now and then later in the course. But anytime you land on one of the infinities for a final answer, we would say that it diverges. Okay, so we'll take a look at another example now, and you'll once again see the setup here is very similar to what we had on the first screen. We'll transition now into the correct notation where we have a limit as t goes to negative infinity of the integral t to 0 x e to the x dx. So once you get to that first step where you change the notation, now it's just integrate as usual. And you guys have probably seen this integral many times by now. It does need to be integrated by parts. So we'll have a u and a dv. We have our x here, our e to the x dx. Our du would be dx. And our v would just be the e to the x. All right, so again, as I continue down now, I want to be careful with what I write, okay? I'm going to change now into the uv minus integral v to u. So x e to the x minus the integral e to the x dx. And many times we've talked about this in the past. As integration by parts is used, you don't really change variables. You can see I've been x all along. This is just kind of a way to organize. And so if I tack on out here from t to 0, that's still relevant since we're just in x's. Okay? So then I'll go ahead and integrate that last part. We still have our limit as t goes to negative infinity, x e to the x minus e to the x. Now it's official that we're going to evaluate from t to 0. All right. Now, much like the last one, I'll go ahead and go through this kind of slow because we want to make sure not to make any careless mistakes throughout. So I'll start with my 0, and I'll plug it in there, there, and there. So that's going to give us a 0 times e to the 0 minus e to the 0, then minus the quantity, the whole thing now evaluated at t. And so, as we take a look here, this first part here clearly goes off to 0. This guy right here, this is going to give us a negative 1. And then coming down over here to this next part, let me go ahead and take this just for a moment, and I'm going to move up here so there's a little bit more room. So let's think about this a little bit. We're evaluating at negative infinity, so negative infinity. So in theory, when I take this negative, really, really big number, that's going to give me a negative big number on the top, and then that negative, when I plug it in here, is going to flip this underneath. So if you think about it, what's happening is we're going to end up with, at infinity, a polynomial over an exponential. That's going to be that t over e to the t. When that guy's negative and I plug it in, that's going to bring it down below. And so because of this, at infinity, and from what we've learned in earlier sections, the denominator is much bigger and is growing more quickly than the numerator, which means that whole piece now is going off to 0. So that's going to be another one of our zeros. And then similar in the sense for this last one right here, we just don't really have to deal with an additional numerator. We could see this as 1 over e to the t, and that's again because of our negative value that when I plugged this in, it would bring it underneath in the exponent. So that also is going to go off to 0. So when all said and done here, it looks like we have a negative 1 for our final answer. And because we landed on an actual number, we now say that the original improper integral converges. So hopefully after working two examples, you're starting to see that most of what we're doing here really isn't anything new. It's just notation. And of course, it opens up the possibility now for us to integrate over regions that aren't necessarily closed, which will now also allow us to discuss some discontinuities, maybe somewhere in the middle of our region as well, which we'll discuss in the next video.